to do is just introduce this notion of the superiority effect of pictures. It increases recall, it increases understanding, it increases attention, and we've known this way before we had our fancy functional MRI machines, which became the decade of the brain in the 1990s. And so I feel in many ways I've kind of grown up with this notion of neuroaesthetics in neuroscience, which is a very small slice of neuroscience, very small. But we've had very smart people thinking about this for a long time in cognitive sciences. The visual part of the brain that I'm interested in is the preconscious. It's called low-level processing or early processing. And it's mute because we're not aware of it. We just do it, okay, all the time. We exercise the power of our visual brain, or not, because it's always a choice. And we can't help ourselves because it's hardwired. And this is the part that I love. And here's the thing to know. With all the information I'm going to be throwing at you, just go back to this kind of mantra. Our brain cells are difference detectors. We compare differences. We crave contrast. Why? Because that's how our ancestors survived. The visual brain allowed us to survive. All of the predators, 50,000 years ago, we still had predatory things. We may have had saber-toothed tigers to contend with. Social rules have changed. But in terms of making sure we arrive safely wherever we're going, that's primarily the job of the visual brain. Okay, the reason I'm so interested in neuroscience is that my background is professional photojournalism. And I've won awards. This one was a state award. You can see I was thrown into sports, into news, all that kind of thing. And I always wanted to know what makes a good picture. And people were like giving me rules or giving me art rules, and it just didn't satisfy me until in the 1990s I really started to understand what attracts our visual brain. Now, the visual brain is a metaphor. We have a visual system. If you talk to neuroscientists, that's what they're talking about, because the visual processing is throughout the brain. Left side, right side, midbrain emotion. It is, a systematic presence. Okay, so what I'd like to do is talk about conceptual science, because there are problems when just explaining sciences, as you know. And this comes from Julio Otino, who did a wonderful article in Nature, and we're going to see 2 magazine covers that he was appalled by. Hates this. Now, I'm not going to explain it because I don't understand it. This is physics. But what he did say, he gave us a wonderful soundbite. And that is, a sensible first rule would be that pictures must not be divorced from the science and scientific plausibility. Images should not conflict with or violate known physics. So when you're a science illustrator, you still have to know the science better sometimes than the scientist. I had in my LSC 430 class a illustrator who's both a scientist and an illustrator, and he can work from home all over the world because he understands what needs to be done. He knows the rules backwards and forwards. He always has work. Another thing, and this came from one of our professors, Dietram Scheufele, and he talks about the problem with things, illustrations looking too real. And the nanolabs was award-winning. People thought it was so clever, but they weren't the scientists or the general public. They were just talking about how creative it was. And Otino says, the image looks so real that it's easy to imagine a viewer being fooled into believing it has already been built. And of course we know that Hollywood loves to demonize science in many ways. Demonize might be too strong a word. But the point is, science can be misconstrued all the time. Example, climate change. Okay. So conceptually, we have lots of challenges. And then there's a notion of how new trends in neuroscience can maybe help us communicate science better, just by knowing how the visual brain works. And that's what I want to talk about today. How many of you have heard of Semir Zeki or read his book, Inner Vision? It's a really good introduction. He was the man who coined the term neuroaesthetics, because in London, when he was looking at neurons and fascinated that consistently there was a neuron that would only activate If the blue patch had a white background, it didn't really look at if it had the black background. This is how strategic neurons, individual neurons can be, and it's consistent. And that made a field grow. But what Zeki did, the contribution he gave us, was that he realized that, you know what, artists have intuited these rules for thousands of years. Okay? Because if you're trying to attract attention, you're going to come down to those kinds of rules that neuroscientists were then playing catch up. So after coining the term neuroaesthetics, it took a couple of years, but he has some wonderful books. 2009, 2014 Chatterjee, I love. As Ramachandran is not on this list, but there are wonderful neuroscientists who care about neuroaesthetics. They care about what attracts the visual brain. And because this is still an emerging field, really the first textbook came out just a couple of years ago out of Oxford University. But for those of us in communication, science communication, we might want to know about some of this. Okay? And that is, again, attracting the attention before we're even aware. That's what the preconscious does. And so what I'd like to first begin with is this notion of the speed of the visual brain. Now here we have Alan Pavio, who is always cited. If you're going to write anything about visual communication, you start with Pavio because he was brilliant in understanding that when you have words and then you have pictures, it's together that they create better memory and recall and understanding. But it's the image that attracts the brain. Okay. Hubble and Wiesel, 1981 Nobel laureates that talked about the visual brain because, and this is what is almost like a cliche, our brain cells are difference detectors. Our brain cells are difference detectors. Our brain craves differences and contrasts. That's what we do. We can't help ourselves. Catch yourself doing that. And it can be conceptual differences or it can be visual differences or mathematical differences. So in getting back to this notion of the speed of the visual brain, let's look at a glance. A glance is faster than verbal processing. Now let that sink in. A glance, look both ways. Can I cross the street? Look both ways. Faster than language. And you start walking before you're even aware that you've answered yes or whoa. A tenth of a second is what this gist is. We call this glance of a scene, and you use it all the time. Watch yourself next time you're driving. It begins memory, although it's preconscious. It's just looking at rough patterns, patterns of patterns. This is what a safe street looks like. This is what a busy street looks like. Okay? But it's unconscious. And we use this all the time. And here's the notion that really amazes me, and I love it. Colin Ware is a computer scientist who writes many of the textbooks that train computer scientists in how to create computer software that people actually want to use. And he says that 2 seconds is a long time in visual thinking. 2 seconds, not 5, not 10, 1001, 1002. That's a long time. You're already bored. You've already got it, okay? That's how fast we are. So let's look at this. Let's parse this just a little bit more. So a glance is faster than language. And 2 seconds is a long time in visual thinking. And the gist starts at, I think the shortest has been the 26 milliseconds. And remember, we've got 1,000 milliseconds in a second. You can find out an angry face. You know you're in trouble pre-verbally, okay? You might not know the person, you might not know but you're like, uh-oh, okay? That's very fast in terms of the gist, but think about that in terms of how our ancestors had to evolve in close groups, and it was really important to know whether someone was angry or not, or friendly, or was cooling off. Our consciousness, recall, begins at 1/3 of a second, 300 milliseconds. So we can do that angry face, but we're not going to identify that face for a long time. So you can go from basically 25 milliseconds, and then 1/3 of a second later. Judging beauty is between 400 and 600 milliseconds. So we haven't even gotten to that first second. So what I like about Borkin in his 2013 is he had science visualizations, okay? And he found, his findings were that people recalled and understood anything with a natural scene or faces or objects. Well, there are particular parts of our visual brain that are trained and centered on processing those. So it makes sense, okay? And we evolved in natural scenery, using tools and recognizing faces. So it was good that he confirmed something in neuroaesthetics, although I'm not sure if he was looking at that exactly. He then tested a couple of years later, 10 seconds. Well, if 2 seconds is a long time, you can imagine what 10 seconds must be like. And what he noted was that semantics, people's ability to discuss the visualization, improved. Well, it would be after 10 seconds if you think about it. I'm not going to go through 1001 10 times, okay? We know that's a long time. But memorability and recall was the same as 1 second. Semantics, not as good, but recall, recognition, just as good. So in 1 second, you are doing a heck of a lot of work, and you might not even be aware of it. So what I tell my students is that if you can be aware of the power of your visual brain, you will see better, you will see deeper, you will see more richly in your life. Because if we don't use it, this kind of stands there. It's a capability, but it's not being developed. So let's go back to some of the preconscious power that we have so that you can use more and be aware of it. We've got the left brain and the right brain. Basically, the right brain is where all the creative fun comes from. The left brain is what gets you to keep your job and make your deadlines and pass your tests, okay? Luminance contrast is what I teach my students in 350. The very first thing is because if I don't, they won't understand color, which is like 7 weeks later. It's preconscious. You can't turn it off. That's what low-level processing means. I used to think low-level was somehow didn't get enough respect. And it's like, no, it just isn't higher-order cognition. Okay? And this applies to color. Color contrast is important. It's also preconscious. Anyone who is an artist who's taken art classes, the first thing you learn is the lightness and darkness of colors. That they have power. That more than meaning is they allow an artistic idea to jump off the page or the screen. And you can't turn it off. Okay? We use lightness and darkness of colors to infer greater depth. Okay? And that's usually what this first talk about that. So let's look at this. Let's show you and prove to you what's important here. Has anyone seen the muffin tin drawing? Because it's not a photo. It was from 1786 from an astronomer, David Rittenhouse.
Can you see well here? Better? Okay.
Is that better? Okay.
Yeah,
I know. Orange on black is terrible. I don't want it to be. Yeah, actually, that's probably. Okay, let's turn this upside down. All I did was switch it, and so the dents have become bumps, and you didn't have to figure it out. Everyone got the right question, the right answer, correct? Because we have brain rules. Okay, we don't even have to think about it. And what I love about is Margaret Livingston. So if you're really interested in this, I would besides Samir Zeki, I would also recommend Vision and Art, the biology of seeing. She's just brilliant. She is a colleague of Hubble at Harvard, and just a marvelous, marvelous neuroscientist and a good writer. She says contrast alone. So I use luminance contrast because luminance is what scientists measure. But contrast alone is enough to give a vivid sensation of three-dimensionality. That's what it does. So you go from stick figures to something with volume. Okay? And artists do this all the time, and they like to play with your mind. And so here we have artist David McDonald, and here's our brain rule. Light from above, okay, and shadows form underneath. That's the dent and the bump rule that we all have. Okay? And it can annoy you to no end. Optical illusions, how many of you are annoyed by optical illusions?
Yeah.
Oh, just so annoying. And half the time I don't get them, you know, and then it annoys me. But what is it doing? It's proving a brain rule. That's why cognitive psychologists like them. Okay, so as a photographer, these are my pictures. I started to understand why I was captivated and really kind of obsessed by the beauty of light. Light and dark and the range of silvery grays in between. I now know it's because we're good at this. It gives us visual pleasure. Okay? It gets us right. Acuity of outside edges. We can see form more easily. So the brain's actually being lazy when it's just looking at the lightness and darkness. And our preconscious brain doesn't care about color. Our preconscious brain only cares about light and dark. It's colorblind. Okay, so the more contrast you have, the more acuity, which is why what's the best way to get people's attention over a long period of time when they have to do a lot of reading? Black on white. Makes sense. Add color and you're starting to make reading a little harder. So let's apply this to science. Okay, so we have the massively large, which is hard to visualize, and then we have the teeniest of small, 3 nanometers, which is a famous toilet that was very important. And then we have a science cover, okay? Look at the luminance contrast before I apply the hue. You've got lightness and darkness. It's not black and white, but there is a lightness and darkness to this color. It's not flat. And then when we add color, you realize how much pleasure there is in seeing this. Why? Because our brain cells are difference detectors. We crave contrast. It allows us to defeat camouflage. And so here are now the particulars of these. Does anyone have any questions? Stop. The one thing is that in explaining nanotechnology to the general public, if you can stay away from the nanolouse, that's a good thing. But the notion that at 3 nanometers tall, this is smaller than the wavelengths of color. Okay? And so human hair, if you're lucky and you have nice thick hair, you're at 100,000 nanometers. If you're more like me, it's probably more like 50. Oh well. But the color blue is between 380 and 500 nanometers. So 3 nanometers tall, it's very hard to conceptualize this. And there is no lightness and darkness at this age. They're adding it, but they're definitely not adding color. So color with nanotechnology is for domain experts who understand. So let's apply this to science communication. And if you want to know more about charts and graphs and what are good charts and graphs, I would recommend Jonathan Schwabish. He's wonderful. He was at a journalism conference, and he was just by audio only, because he didn't want to fly out to DC to Madison, Wisconsin, and we were so happy to have him have his voice. And it's a wonderful beginning article. Dietram likes this article too. He's using it, but he's not talking about neuroaesthetics. Okay, he's just using the rules. And look at it up here. He says this is bad and this is good. Why, do you think? Because this works with the brain. It's contrast. It's luminance contrast. You don't have to get fancy. And so these software programs that allow you to make all these kind of fancy bars and charts and let's add depth and all of that, check out neuroaesthetics before you get into all the fancy stuff that you can do with software. This is more effective. It goes the way the visual brain is doing because of the luminance contrast. Okay. Here's another example that he did, Schwabish. Now again, I'm adding the neuroaesthetics, but I looked at this and he said, this is a bad graphic. And I was like, yeah, it's cluttered, nothing stands out. And so his correction, can you see the contrast? The luminance contrast? It's working with our visual brain. And that's something that's really still kind of emerging, this consciousness.
I have a question.
Yes?
There's still light drop shadows on that bottom one. Is it to make it more engaging, or?
I don't know. He just
if you
did.
have the drop shadows,
He
would
just.
higher contrast.
Yeah, actually, I would have increased the contrast even more. I agree. Yeah. Any others? Thank you. And then he's got his spaghetti chart. He doesn't like color because he says, you know, revising this, he's working with contrast. Black against gray and white. That's how simple the visual brain is. The visual brain did not develop in Technicolor and movies and all the wonderful things that distract us all the time. Okay, it was, where's the tiger? I hear the roar. Where is it? Let's start moving. Okay, and you are not dealing with color, you're dealing with lightness and darkness. let's get into this. The amygdala is the seat of the emotional brain. How many of you like scary movies? You really like them. Great. How many of you hate them? Hate them. Yeah, my cognitive brain doesn't care that it's only a movie. It's like, don't go there. What are you doing going there? Okay? I just believe it better. My visual brain, I'm very visual. The amygdala is always asking one question, am I safe? So if you go into a particular room, let's say classrooms, and you feel very safe, you can feel yourself relaxing. But if you're going into classrooms that are not safe, you know, maybe they're really hard, you're worried about your grade, that kind of thing, the amygdala is giving you those signals. You're not really safe. Look around. That's what the visual brain did. It kept us safe. And I hate this picture, and my students are always sending me a picture like this. Okay, kill the little precious little bird. But that's what our ancestors had to contend with. It was survival. We didn't live that long. So visuality was not a luxury to go to use at museums, even though I think going to an art museum is one of the best things you can do. Visuality was about survival. It was about camouflage. Okay. And artists can still do this. If you are interested in really creative art, the Chinese artist Lu Bolin is amazing. He's on the map artistically in Europe, and I hope here in the States too, because he's playing with our mind. When it comes to the fact that the first thing our visual brain does is try to defeat camouflage. Okay? And contrast is not a way to do it. You don't do it with contrast. Contrast is what makes you see the tiger in the grasses. Okay? But to see this little creature here, he's just blending in with the background. That's what camouflage does. And we knew this. Artistically, we knew this. So this comes from about 30,000 BC, Chauvet caves in France. Let's move that up, actually. Let's go back here. So what can we see? That we like lines against an easy background that forms shapes. We like faces. We are face-seeking. Okay, so the luminance, the contrast of lines. Very simple things, but with the visual brain very early on. Let's look at face-seeking, and I want to ask, any of you know Beth Doolittle? Okay, I want to ask you what you see. What are you seeing?
Faces.
Are you seeing it?
In the rocks, in the trees.
Try not to see the faces. Try not to see them. Just look at it. Just look at, you've got two cowboys and horses.
Right.
Don't see the faces. You're seeing the faces, aren't you?
No, no.
You cannot see the faces. So my favorite face took me a couple of years to see this beautiful face with the birch trees. Anyone see that?
Yeah, right.
It's just gorgeous. Faces here and here, and you know, they're just everywhere. There's at least a dozen, and I'll have my students come up and point them out and things like that. And you can own, you know, a copy of this print, and you can still be seeing more faces. Like I was seeing them today as I was preparing for the talk. I'm like, wait a minute, these are parts of faces, you know, these trees and that kind of thing, the pebbles. We can't turn this off because face-seeking is looking for predators. And the predator that is false is fine, who cares? But the real face that you miss could mean you don't have children. You don't pass on that DNA. Okay? So we descend from people who are really good at looking for faces without even knowing about it. That's what we do. It's face-seeking behavior, and it's pre-conscious. It's called mid-level processing. And faces are a pattern of patterns. We make a lot of patterns. We're seeing them mostly for depth and where are we and that kind of thing. Am I safe? But the mass media, these are my pictures, the mass media always could look for a beautiful face or an unusual face. And so to extend our definitions of an interesting face is something that artists and photographers do all the time. But I didn't know when I was doing this that face-seeking is something I can't turn off. So in science, I would suggest we need more faces. Okay? We can't turn them off, even if they're pretend faces. on that, even if they're background faces. We need more biographies. We know, we're starting to learn that if you get wrapped up in someone's story, that narrative transport is what allows you to understand their story. So you can understand complicated science because you're following a person's journey through that science. Okay? And that's what we're studying in 430. Okay, now you're ready for a chart. And I'm sorry, this is a really terrible chart on the brain. But what I wanted to do is just to prove to you that when I'm talking about the preconscious brain, I'm not making this stuff up. It comes from Margaret Livingston, and again, this was the only thing I would have her redo if she ever asked me. It's the notion that the visual cortex in the back of our head, okay, that's where it is. The where system is what's going to come up. It takes a third of a second to get to the parietal lobe, which is the top of the head and which is about consciousness, where everything's put together and we see it. Motion perception, depth, spatial organization, figure ground segregation, all these patterns is what we do. Color is not there. It's just lightness and darkness. And then the what system at 300 milliseconds is the object of face recognition, color perception, and there are parts in the what system that are just devoted to doing that. So when you see something, when you see a work of art, and you study it, you are using different parts of your brain all over the place, but yet you're seeing one image. How does that happen? Well, neuroscientists haven't figured that out. They call it the binding problem. They don't know how we just see that one image, even though it's being processed throughout different parts of our brain. They're just happy that they know those different parts and what they're doing. And again, judging beauty, what you like, what you don't like, what you're interested, really fast. How many of you felt guilty going through a museum and just going like really fast and saying, no, 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 no. You're doing it well. 10 seconds isn't going to change your mind. Okay, it'll change your semantics, but it won't change your mind. Okay? Is this a tragedy? Of course not. Because another brain rule is that the brain assumes three-dimensionality. It assumes 3D. It assumes that this woman has a head. She's not some freak and she's not a victim. It's a funny picture. That's a pleasurable optical illusion that I think we need to understand, is that we're very good at depth. But it can be highly cultural. After this, it becomes highly cultural. If you want to be communicating to people outside the Western cultures, occlusion, which is what this is, the fish is occluding the woman's head, that's universal. That can be understood by children anywhere in the world and by cultures anywhere in the world. But depth, it becomes very much cultural, what our experiences are. How we live in a deep world is culturally determined and experientially determined, and how we live in a flatter world. That doesn't mean one's better than the other, it's just what it is. So that's why I tell you that if you're aware of the power of your visual brain, if you want to live in a deeper world, you can, but you got to work it if you don't automatically do that. Okay, let's look at depth. Okay, how much time do I have? Okay. What do you notice your eyes doing? Okay, so just, there's no wrong or right answers, just kind of watch yourself watching. Because again, it's preconscious, you can't turn it off. One's more annoying than the other. What are you watching your eyes doing? Especially with this one. This is the easy one. The most annoying, probably. What are you doing? Yes?
My eyes tend to oscillate between two contrasting images back and forth, back and forth.
And you're trying to solve, yes, your eyes are oscillating, and you're trying to solve a problem, right? A visual problem is this doesn't make sense. If I look at it more, maybe it'll make sense. Where am I missing? What am I missing? What this is proving, this optical illusion is proving, is that we are following lines. We are trying to make sense out of following lines. This is a more artistic, impossible object, bless you. And you can't really have this in real life. It's really something that only can be drawn. This is the devil's fork. And it's because of ambiguity of depth that we can't figure it out. But yet, look at this and don't try to figure it out. Stop your brain from following the lines. Just look at the fork. You're following the lines, aren't you? Probably who you are. If you're being really honest, you're like, okay, just a little bit, I'm following the lines. I'm trying to figure this out. Because what we're hardwired to do is to follow lines. And that's what we do preconsciously. So if you want to work with the visual brain, be really careful about lines because we'll believe them, we'll accept them. Let's apply this to an information graphic. And we're entering, you know, in 1 year, and we got 40,000 units of something. Problem is, this is the same data, but it has the context. So this looks dramatic, like if this was your retirement account, you'd be, you know, trying to apply to McDonald's as soon as you could. You'd be broke. But this is the context of like, oh, it's just a dip. Look at all that we have on that. And so look to see, and you see this a lot in the financial pages, and they assume our readers already know, but if you want to be professional, you include the broken axis. It starts at 4,000 and then there's 0, or what's called zero basing, in that we show the 0, so that you can show the context. This has no context. All it has is drama. The same thing about lines. We follow them. We don't even really notice them because we're primed to follow them. We're not. Preconscious is not about cognition. Because if you're preconscious or unconscious, you have to recognize something before you can start thinking about it. So we accept these lines very quickly and easily unless we've been trained, you know, and really trained our subconscious. But the same data can look dramatic, or it can look like, oh, this is not a big deal. You can slow it down just by the width and depth of the tick marks. Okay, bless you. So this is important to know, that we have a propensity to follow and accept the lines. So it's our thinking brain that keeps us honest. Or can critique a chart or graph that isn't honest. So think about zero basing if you're working with a lot of these timelines or fever charts. Okay, another thing to try to watch yourself watching. Okay, what are you doing?
Getting hungry?
I'm getting hungry, you're right. Our brain cells are difference detectors. What are you doing?
Okay.
You're comparing, looking back and forth. Kind of feel like a ping pong ball. And you're just doing it. Sometimes it's pleasurable, sometimes it's annoying. The greater differences is greater attention. The very tiny next to the really big. And this is from Stephen Kozlin, who was a cognitive scientist out of Harvard in the 90s. And so this can give you visual pleasure, or can actually, who's the guy who lost all the weight by eating somewhere?
Jared.
Okay, you know him. Where was he eating?
Subway.
Subway, okay. Okay, very easy, works with that preconscious brain. The very big and the very little, okay? Our brain cells are difference detectors because that defeats camouflage. Camouflage we don't like, unless it's a fashion statement. Okay, so easy to compare differences. Size differences in this case. You can start to see how big Alaska really is. You probably already knew that. Let's look at Africa. Look at the nice bold line. Our brain cells are we're difference detectors, but the nice bold black line on a white background, easy to see. And then if you're interested, you can start to see, my God, there's China and the United States, and we still haven't filled up the outline. So you work with the visual brain. This can be seen also in Jonathan Harris. You've probably used some of this software. But let's go back to the notion of why using this software. It's about storytelling. I use computer science, statistics, storytelling, and visual art as tools. I believe in technology, but I think we need to make it more human. If you want to make anything more human, tell a story. The free is the Wordle, which we use probably a lot. And it's based on size differences. What we just showed with the hamburger. And it carries information. And you get it very easily because that's what the visual brain does. So when you're in the hands of an artist, you have David McCandless, and he has some beautiful books. If you like information graphics, he has beautiful books. Information is beautiful. Based on that notion, it's not his notion, I'm applying the neuroaesthetics to it and saying this is also why it works, is that brain cells are difference detectors. Because I like art rules, but art rules don't tell me about my brain. They just tell me rules that I have to remember. If I can understand my visual brain, I can go many more places and see more deeply. So let's look at these. In this particular thing, this is about snake oil versus stuff that really works. So you have your difference detection, top and bottom, big and small, dark and light, tall and narrow. Okay? Just to understand that can make you a better consumer and editor of any kind of visualization. You don't have to understand the science, you can understand your visual brain. Again, that pre-conscious part of it. There's much more once we get conscious. And so here's my last example in terms of applying this. And this came out of Science Communication, and these authors were revisiting, Wells and Murray, they were revisiting this information graphic came out of a software program, and it's talking about the polarization of political parties. And it really kind of looks like they're duking it out, right? The red and the blue against each other, in your face kind of thing. And then they decided, well, let's look at the software. What other choices did they have? So Adamic and Glantz were kind enough to give them their data, and then they reran it, and you can see all the options that they have. And then, based on the findings, they chose that this was a better discussion about polarization because it slowed it down just a little. There was a little more closeness, and they could talk about the gap, and it didn't look too much as much like nuclear, war on this. So, in terms of a sophisticated computer science world, we have so many powerful programs. You can still understand the visual brain that can give you an edge. Okay, the stuff you can't turn off, the stuff that happens before cognition begins. So let's take some takeaway points. Let's talk about that and understanding the visual brain. The first thing is that what I've all been talking about is primarily the WARE system, which is the first thing that the visual brain is doing, and it's before identification, it's pre-conscious. Neuroaesthetics is emerging, okay, but it is supporting what master artists have known for thousands and thousands of years. Artists learn by trial and error, or they learn from their culture, but the very best art is playing on the visual brain. Understanding this pre-conscious visual brain, difference detectors, okay, luminance and contrast. Get that because you're so good at it. Face seeking is hardwired. Start to notice all the faces you see in clouds that aren't really there, and then try to turn it off. The lines and outside edges, the power of the brain's ability to follow a line to its conclusion and accept it, because that's how we create shapes. So in terms of those line graphs, a lot of mischief can be hidden because we accept those lines. And then that back goes to the conclusion. So those brain cells and the luminance contrast. And then the low-level processing rules, again, many people call these attention magnets because they magnetize attention. We just do it. But it's not that well known how powerful our visual brain is. Again, process before you identify it. You identify it about a third of a second, but your brain's been very busy before identification. Okay, so I think we have some time to talk. This is my class that's online, Visualizing Science and Technology, and it's for 5 weeks. So you can be anywhere in the world, on the planet, as long as you have access to Wi-Fi, and if you don't, then you can't take the course. I just want to make sure that's clear. I've gotten questions. I'm going to be in the Peruvian farm fields. Can I take your course? It's like, not if you don't have a coffee bar nearby. It's good for 5 weeks, okay? It has a graduate component, and I'm Shiela Reaves. Okay, so thank you.